Hello, how's the sound? Cool. So first, I'd like to briefly mention my co-authors, Yuri and Ben, who played an equal part in doing this work. But first, I'd like to say I was really interested to see this list of keywords from the open-in. I was particularly interested because my paper actually hits most of the negative words. This is a verification paper rather than a vulnerability paper. The last two talks were great, vulnerabilities are great, but maybe if 13 years ago there'd been a few more papers on verification and proofs, there would have been far fewer vulnerabilities in today's USENIX. Okay, so what am I going to talk about? I'm going to talk about a framework for modeling distance-bounding attacks. And the big contribution of this work is to put some kind of order on all the distance-bounding properties, tell you what symbolically is good to check, and symbolically how can you check protocols in an easy, automated manner. And I've got examples of contactless EMV and a distance-bounding protocol which has been patented by Philips. So first, why should you care about distance-bounding attacks? Well, one answer is they are incredibly powerful. Right now, any passive authentication system can be beaten by a distance-bounding attack. So this is a video from Birmingham of someone who woke up to find their luxury car had gone from their driveway. Luckily, they had CCTV, and this is what they saw when they reviewed the video. Now, it's really common to leave your key fobs by the door in the UK, and that person by the door is sticking a device through the mailbox, and they're relaying the car key signals to open the door. Now, these aren't the best criminals because they've forgotten to start the car. So now this person needs to go back and relay the signals again to start the car. And right now, there is no kind of crypto at all which can stop this. You can have as much crypto you like on the key fob. You can just relay the signals. There is really no protection against this right now. Next year, we might get some. Oh, and once the cars start up, they don't need the key to be present anymore. So these people can drive the car away to wherever they like. This actually happened in Birmingham, where I work, just down the road from our department. So when we saw this, the first thing we did is went and checked all the PhD students to see if any of them had a new luxury car. And this is actually the equipment they used. The police later caught some of these people. And as you can see, a big detector to put through the mailbox and take these systems. Another example we've been working on is contactless bank cards. These are very popular in Europe. It's an extension of EMV. You just touch your bank card to the payment terminal, and it takes a small payment. Really convenient. Don't need to type in a PIN. It's great. I realize it's not so popular here yet. When I was first here, I tried paying by just tapping my card against the payment terminal. And the shop assistant looked at me like I was some kind of idiot and explained how to swipe it. But it'll be here soon. So how it works, these cards have a shared key, a symmetric key with a bank, and a public key. The core of the protocol is the shop reader sends a UI, a unique number, a random, a nonce to the card, along with some information. The card generates a session key based on the number of times the card's been used and a secret bank key. It uses this to make a MAC, which is proof of payment, and it signs some data the card can read. The shop terminal checks this signature. If it's the correct signature of the nonce and the amount, it accepts it, and it sends the MAC to the bank as proof of payment. So that's the core of all these protocols. Each card company has a slightly different main protocol. Here's Master Cards, which adds in some housekeeping. But the core is simply send a nonce, make a MAC, and sign it. However, this protocol is fantastic for being relayed because almost all of these steps can be cached or done out of order. So if I want to relay this card to the shop with a couple of phones, I can start the session with the card first, and then I can send the data for the relay before it's needed. I can do this with everything apart from this one random number, and that's the only thing I have to properly relay. So actually, there's a very little amount of time added to relay this because of the design of the protocol. Even worse, the one step you relay requires the card to do a lot of crypto, which takes a very variable amount of time. It's very hard to predict how long a smart card will take to do crypto, so easy to relay. This is some experiments we've done. And proof of concept, there's a bank card under that phone. We can relay it to this terminal, no problems whatsoever, because the variability in the time it takes to do the crypto is bigger than the relay time. Slightly more realistic scenario, a damp day in Birmingham. We can actually read it through a card or a wallet. So this is quite a danger. One person can hold a phone near someone's bag and relay signals to a terminal live. There's some literature from the card companies saying this isn't possible, but as you see, it absolutely is. So there are currently lots of designs to stop this, but no actual implementations. MasterCard have a system which they use to stop this, and what it does is it introduces a new command which just does a very fast nonce exchange without any crypto, which can be timed accurately to detect a relay. And then the crypto comes later after this time step. So putting in a time bound can actually actively stop these. NXP also have a similar protocol. Unfortunately, they're not telling anyone what their protocol is, or if they are, they're making them sign non-disclosure agreements. However, a bit of digging, we found NXP had patented a protocol. So we can't say for sure this is their protocol, but this is the protocol they've patented. On the downside, patent documents are the worst thing ever to read. This is a typical paragraph from a patent document. I read that about 5 times. I have no idea what it meant. But after going through the patent document in great detail, I managed to extract a protocol from it, which looks something like this. Again, there's an exchange of nonces. One nonce is sent to the card. Very, very quickly, as fast as it can, the card replies with its own nonce, and that is timed. And it's got to be below some threshold which is given in the protocol. For authenticity, MACs are exchanged to make sure no one's cheated in the protocol. So that's the kind of... and only some versions have that timing information. And this step is often split into 8 single-byte steps, and the average is taken. So that's the state of things. We have these dangerous attacks, we have these possible defenses. So the questions our work addresses is how can we model these? How can we say, are these protocols secure? Which raises the wider question, what does secure even mean in this case? And how can we test that? And again, we're working in a symbolic framework here with a dollar-the-hour attacker and abstract protocols. So our answer to that is a little modeling language we can write down protocols in. This is based on the applied pi calculus. Full details and explanation of all this in the paper, but very briefly, we can write down protocols which do inputs, outputs. These expressions can let us specify things like encryption, decryption. And importantly, for that timed action, we have a start timer and a stop timer action. We also need to specify the locations of processes. So we have these square brackets to say this process is at one location, or maybe they're at separate locations. So what we would like is for a correct protocol, if we have a card and a reader at different locations, the protocol should refuse to work. Same location, it should run. Now, using this language, we can model the protocol I just showed you. It looks something like this. Again, full details of what all this means in the paper. But particularly, we can write down in this model, we can specify an unbounded number of identities. Here, this means an unbounded number of new identities running an unbounded number of times. So we can specify an arbitrary number of cards running an arbitrary number of times. Similarly, we can specify a verifier, the shop reader, and the protocol, and we can say this shop reader does a verify event if the protocol believes the card is close. So now this gives us something we can test. So a word about the semantics, full semantics in the paper, but the semantics of our language is based on the observation that if two things are at the same location, we can do a challenge and response within the time limit. If they're at different locations, we can do the challenge, but the response can't get back in time. So our semantics says when the timer is running, you cannot receive outputs from remote locations. And just that one thing is enough to give us an accurate behavior of these cards. We don't need to model exact times. We don't need to put time measurements in it. And that's what makes this tractable. That's what means we can do all the analysis. So there's a semantics to do that. But again, that's probably too much for a talk. So please see our paper for details of that. So the next question, what is correctness? Well, in the literature at the moment, there are 5 different definitions of correctness for these protocols. So it's a bit of a mess. People are proving protocols correct against one, fail against another. Part of our work is to show the relationship between these and match them to different attacker scenarios. What I showed you, I can write down like this, known as a relay attack or sometimes a mafia fraud attack. 2 locations, an attacker at one simply broadcasts messages to another. That's the kind of classic relay attack. Another popular attack in the literature is known as a distance fraud attack. This is a slightly different attacker. Here I've got a card or some kind of prover who's dishonest and is remote from a reader and is going to try to trick the reader into believing they're close. A different kind of attack. A variation of this uses a dishonest remote party who will try and piggyback on some local party. So what you could have here is the local party could do a proper exchange of nonces, and then this bad remote person could insert their ID after the distance check had passed. Another variation, known as terrorist fraud for some reason which really isn't clear, we have a dishonest attacker who won't share their long-term keys, working with a local attacker. So then the question is, can this dishonest party, working with this local attacker, make the reader think they're close without revealing their long-term secrets? A variation of this adds in other dishonest attackers here who can help, and that gives us 5 different definitions from the literature. So the first thing we want to do is be able to write these down in a way we can test them. So if we take this simple relay attack, we can write this down in our calculus, in our modeling language. We have one location on one side, another location on another side. We have the verifier process, which I put up earlier, which represents the verifier. We have some collection of provers who we're trying to test at the remote location, and we have these arbitrary A attacker processes. So that formula represents this attack scenario. And what we can ask then is there any process A which makes it possible for this to reduce to the verified command? Is it possible that this attacker process somehow tricks this verifier into believing the process is local? And this is something we can test using tools, mathematically, show to be true or false, show that this protocol is secure against these attacks or not. Likewise, we can define a dishonest prover process, which leaks all its secrets, and then we have this equation where we ask, is it possible for an attacker in that scenario to trick the verifier? If not, it's secure against distance fraud. Otherwise, a distance fraud attack exists. Similarly, with distance hijacking, we add in this honest prover here, which can be used, and that gives us an equation for distance hijacking. And terrorist fraud we can represent in the same way. So now, with each of our equations, we can write down the attack scenario as an equation in our system and test it. So that gives us 5 different properties, which we can now test, which is great, but it does nothing to tell us which is the right one to use, what's the relationship between these. So we can start to compare these properties by thinking about the building blocks of our system. We have an arbitrary number of cards, P. We have the verifier, V. We have an attacker, process A. And we have the other provers, ID prime, who we're not interested in, but could be somehow abused by the attacker to get the protocol to work. We also have this other class of dishonest attackers who are going to try and cheat, lie about their distance. And we have dishonest attackers which the verifier isn't trying to check right now and could kind of be additional parties to the attack. And we can actually now express an order on these. We can specify their semantics, we can order them. So clearly, nothing at all is the weakest, and an attacker can do more than nothing, obviously. Honest cards can do more than nothing as well, but there's no link between the attacker. Some things the attacker can do which honest cards can't, and the same in reverse. Both of these together is clearly more expressive, and the terrorist attacker is more powerful, and the dishonest attacker is even more powerful than that. So we have an ordering on these processes. We can also express equalities between them. So for instance, adding in dummy cards here has no effect. So this equation is exactly the same expressive power of this equation. Now we can apply these rules to express an ordering between these properties. And we find that mafia fraud is strictly weaker than terrorist fraud, which is strictly weaker than assisted distance fraud. Likewise, distance fraud is weaker than distance hijacking, but these two classes are unrelated. There's nothing between them. So now we can continue this game and consider all possible arrangements of these blocks, and we're led to all of these unique different properties, including ones we haven't seen. However, some of these are a bit odd. Some of these aren't really that different. For instance, if you have a terrorist attacker who can't send their secret key but can do everything else on their own, and a distance fraud attacker, the only way we can distinguish these is if the verifier reacts if the private key is sent to it in the clear, which would never happen. You could define a protocol that way, but it's not going to happen. So we can add heuristics and get down to this ordering of properties. And we have 2 more in particular, which I'd like to point out, which we've called new properties, which we've called relay hijacking and uncompromised distance bounding. And the first one has compromised cards at both ends and attackers trying to relay a card which is the target card. We also have relay hijacking, which is attackers at both ends, one of which is using dummy cards. So now, given this framework, we can actually start to look at different pieces of it. So this section here, that grayed out section, all uses terrorist attackers, which I think is a very strange attacker model. It's an attacker who could send their private key, but chooses not to. So to me, that's really an unrealistic attacker model, which means this new property of uncompromised distance bounding and distance hijacking are the most powerful properties you could consider. So this section here is remote-only attackers. So if you have remote-only attackers, distance hijacking is the property you need to check. This section here has no compromised hardware. So if you believe your hardware is correct, then relay hijacking, the new property we define, is the security property you want to check. And this section here is the part of the graph where the target device has not been compromised. So if you think about EMV or car fobs, if you've compromised the card, you can clone it, no need for protection. So in the case of EMV, it's this new property we want to check as correctness. So this tells us what we can check. Very briefly, we can translate our calculus into the applied pi calculus, which gives us a tool where we can just run and check. A little short of time, so I'll skip the demo, but we can just run this tool and it will tell us this protocol has these properties. Some results, various payment protocols, we find some attacks and some are okay. These are all new attacks previously undiscovered, but these distance fraud attacks probably aren't really applicable to the EMV attacker model. So aren't that surprising? We do find an issue with NXP's protocol if it uses a shared key. There's an attack where you can insert your identity at the wrong time. So that is an issue. NXP's protocol would not be considered secure if it uses a shared key. It needs a unique key per device. Okay, so that's really my talk. I want to make the case for verification work. It really is the way to avoid a lot of the vulnerabilities we've seen. This gives us a complete tool set for doing distance-bound attacks. And if you ever have a passive authentication system, please do consider distance-bound attacks. They are remarkably powerful, but they can be stopped by the kind of methods I've presented here. Thanks.
Thank you. So we have time for a couple of quick questions. And I see there's no one there, so I will ask one. So I have a question about the proofs on the distance attacks. So the assumption here that you're making that the amount of time, if you're a relay, is going to be at least the amount of time required to send the message to the to the device. But that may not be true. That's true certainly if you're doing this, if the attacker is doing this by reading the entire message, relaying the entire message, and so on, a step at a time. But if the attacker can be more granular than that, for example, if their relay is being done in the analog domain, so it's essentially sending the signal that is coming from the card and so on in almost real time, bounded kind of only by the speed of light of that propagation, then it seems that you would need very, very tight bounds in order to detect that there's a relay at like the nanosecond level. And this would probably break down then in practice?
That's a fair point. This is based on the assumption there is some time bound. You can say this distinguishes local from distance. It may well be the case that your hardware isn't quite good enough to actually detect that.
Right, so, but if you're doing it in the digital domain, then you're pretty comfortably safe. Yeah.
If you can just say, here's a time bound which will provide a limit, then all this works.
Right.
If there's no time bound, then you may not be able to implement the protocol.
Okay, thanks. Any further questions? Okay, join me in thanking the speaker.